Hello everyone and welcome to the third video in my AX-60 restoration series. And today we're finally up to the power supply, or should I say, this year we're finally up to the power supply. It's taken so long for me to do this video, it's almost embarrassing. I think I finished the power supply about 18 months ago, maybe even 2 years. First test, I had forgotten to do something, so I went back and got the board remade again. And then from that point, life just got in the way, and I moved on to some other stuff. So finally, I'm back to doing it again. And in fact, I'm doing 2 power supply videos in a row. So I'll be doing this one and the OBX power supply video. So if you're a subscriber, you're probably thinking, well, where's the OBX power supply video? Well, yeah, I'm doing it now at the same time. So hopefully we can get these 2 out of the way. So, why are we here? Well, we're here because the AX-60 has a fairly common problem in that eventually they have trouble tuning. Now, this can happen for a whole lot of reasons, and I suggest that you check the normal stuff first, like power supply, and those CMOS chips, those 4051s. So if you have problems with the tuning, check those CV, those sample and hold storage lines that take the CV from the CPU to the voice chips. So check all that stuff first. If at that point it still fails, yeah, chances are it's the supply itself. I've had some people confirm my thoughts since the last video, and one viewer in particular, Normand, I think his name was, he followed my suggestion for the negative rail. He made his own minus 6 volt supply, and magically his AX-60 started tuning as well. So mine did the same thing. I redesigned the supply, I put the new supply in, and like magic, all these old CEM 3396s, I think they are, the voice chips, all these old voice chips just tuned magically. It was amazing. I have a few theories on why. I thought it was because the CEM chips were aging, and that AKAI had not quite starved them on the negative rail, but they had definitely not followed the recommendations for the supply. And so I thought, well, okay, they're getting a bit old and they need a bit more juice, and that supply just was never designed to give them the right amount anyway. So it all made sense that when you put a new supply in, that all of a sudden it just works. But I think it's more than that. I think it's the supply itself as well. Yeah, I'll go through it in a lot of detail. We'll look at the schematic, then we'll look at my schematic, and we'll go through all the differences and all that kind of stuff. Now, if you want to do this same mod to your AX-60, I will put all the schematics, the board files, the Gerber files, everything on my website, and it's just free for you to do whatever you want with. So you can modify it or get it made exactly how it is, or do whatever you want. I'm just handing it over. I've done a supply that works. It just fixes the faults in the original supply, so it's not like a complete redesign or anything. There's a couple of things I've added to help disperse the heat. I will start talking about thermal resistance in this video a little bit, but I'm planning to go into it in great detail with the OBX. So the OBX is a wonderful supply to explain thermal resistance and how you calculate heat sinks and how you distribute the heat that you must dissipate to get down to the right voltages. Now, AKAI weren't as good with that. They did a fairly good job in a basic way, but then there was a manufacturing mistake where on one of the Zener diodes that they use for the less important power rails, they covered in a tube, in a plastic tube, where they were only supposed to cover the legs of the Zener diode, not the whole Zener diode. So it can't remove its heat. It's trapped inside a blanket, and so one of the more common failure points for this power supply is the Zeners. One of the Zeners overheats and dies. So yeah, I've worked around that with my supply, and in fact I've tried to redistribute the heat somewhat. But again, I'll need to explain that when I have a look at the schematics. So the point of today is we're going to take this old supply, like this, and we're going to turn it into this. Now, this is a slightly older version of my supply, but basically we will make that. So I'm not going to go through step by step. If you're going to work with power supplies, I assume a certain level of competence with electronics. So this is not for the absolute beginner. And consequently, I'm not going to explain the nitty-gritty details. There'll be a BOM on the website, so you can just source those parts and go and make it yourself. But I will explain how the power supply works, just not how a beginner should build it. So you'll end up with a board like this that you'll start populating, and then you'll need to take some of the old parts off the supply, like the connectors and the heat sinks, and then reuse them on the new board. We should be able to source the connectors. Again, most connectors are still available. Not many of them are obsolete now. I think some of the older ones in the Oberheims are starting to become obsolete now, but these ones we should be able to find if someone could source them. But in my supply, it allows you to reuse the connectors that were in the existing one. So yeah, not everything will be in the BOM. You'll need to reuse some parts, but I'm sure some smart people will figure out what part numbers the connectors are and stuff like that. So if you do, put it in the comments so everyone else can know. What else? Anything else before we start? No, just an apology about how late this video is. I really did take quite a long time. There were a lot of people waiting for it, and some of them even sold their AX-60s while they're waiting for me to do the power supply video. So, whoops. But having said that, there's heaps of people who are still stuck around, and thanks for the reminders. There's been numerous reminders that I get constantly, and so thanks for your patience. So let's get started. Okay, so here is the schematic for the AX-60 power supply. Now, this wasn't an overly expensive synth. It wasn't designed as a top-tier upmarket synthesizer. So the first thing you'll notice is that we have different transformers for different markets. Now, this saved cost. On the more expensive synthesizers, or at least when the manufacturers decided to do us a favor, they would actually put in transformers with multiple primary windings, and you could just wire up that the different primaries for whatever voltage that country had. But in the lower tier synths, that would be a waste, because you'd have a bigger transformer where only one primary winding is ever used. So to save money, they would split them up and have lots of different transformers for each country. So each individual synth cost less, but there's just a bit of a mess if you needed to ship one around the other side of the world, which is what happens very commonly now. So in one of mine, I've replaced the transformer already. Okay, so our transformer gives us 2 AC voltages. Now, the only real reason is so we have a separate analog and digital supply. Usually that's the case because digital circuits tend to put a lot more noise onto the 5-volt supply than analog circuits do. So you generally don't mix them because the fast switching of the digital circuits tend to put a lot of strain on the digital supply. And we like our analog supply to be cleaner because we're looking at the differences between varying voltages that go up and down. So we're very concerned about the smoothness of that. So we tend to split them up. And also it's just how much power do you want from each rail. You may have different components that are rated differently. The main regulating component, or the component that does all the work in the 5-volt supply, is this one. So this is just an old germanium transistor, and it's controlled by this regulator here. Now this is not a 5-volt regulator, it's just a variable voltage regulator, and there's a divider here which sets the feedback. So this is where we would set our voltage. So that's been set up to give us 5 volts. There's some filtering on the end of that, and this is an interesting one. This is our first Zener diode, and this part of the circuit already supplies our 5 volts. So it's strange to have a Zener. There's also a 5-volt Zener on the same line. Now usually you use one or the other. You use a regulator that will give you 5 volts, or you use a Zener that will give you 5 volts. So I'm guessing that this is a backup. And I had a look at this Zener, and I think it's 5.1 or 5.2 volts. So it's slightly higher than the voltage coming from the digital supply. So I'm guessing that this just might be a safety or a backup. And when I look on the power supply, it looks like this diode isn't getting very hot. So there's no way that it's regulating the voltage that goes out of here. Because the thing about Zeners is to control the voltage, you're effectively splitting the current 2 ways. So the current will go through to your digital supply line, but the shunting voltage, which keeps it at 5 volts, will end up going through the Zener. So any higher voltage coming into the Zener will have to be shunted through it. So for this to keep proper voltage, it would get pretty hot. In fact, this would have the same current through it as whatever the circuit is that it's feeding. And this looks like it's hardly used on the main board. And on one of my boards has that fault where they've put this Zener diode in a full tube, and another one of my AX-60 power supplies have it configured correctly where the legs are in the tube only, and the Zener itself is free to dissipate heat. So one of them's been done wrong, and that tube is still clear, so it's not black. So I know this is not being used very much, so it must be a safety. I've never seen that before, so I mean that's pretty cool. Give them credit for doing this part of the circuit right. Not much else to say about that one, except again, I think that viewer I was telling you about, Normand, he found that the 5 volts analog supply and the digital supplies are actually tied together on the main board. So we'll have a look at that in a minute, but for now we just consider this a separate supply for our digital chips. Okay, so moving on to our analog supply, we have a bridge rectifier again. We've got our main filter caps, and our 2 main regulators here are what we would normally expect nowadays, like a 7815 and a 7915, except these are the M versions. The M versions, they're only 500 milliamps. So I've actually changed these in mine to be 1 amp. So you won't find the M on the designations for in the BOM for my supply. So that helps a little bit. These are actually okay. These 3, so this regulator, and this transistor, they're all sitting on the main big heatsink. So if I show you, I'll just grab it here. I'll probably go out of focus, but you can see these 3 here. So there's that transistor for the 5, and this one is the 7915 negative, and this one's the positive 7815. Now the heat coming off that heatsink mostly comes from this transistor. If you have a look at the voltage coming in versus the voltage coming out, it's like 8.9, so it's nearly 9 volts. And coming out, it's 5. So there's a 4 volt drop across this transistor. Now this transistor, I think in the data sheet it could supply about 2 amps. So there's no way that it could get to the full 2 amps because, I mean, that's already dropping 4 volts. So even at 1 amp, that's 4 watts. At 2 amps, that's 8 watts. That's massive. And also the data sheet isn't clear on its thermal resistance and how to do those calculations. So the older data sheets tend to just say a maximum amount of watts that something could handle, which doesn't necessarily tell us a lot. I was able to find out that by itself without a heatsink, I think it's about 1/4 watt before you get into trouble. And with a heatsink, it was about 5 watts max. So if we're dropping if we're dropping 4 volts at 1 amp, we're already 4 watts. So yeah, a lot of the heat's going to come from this guy. These two, not so much. I've increased them anyway, so they're now 1 amp each. But it's interesting to note that most of our heat comes from that component. So we move on to the lower voltages now, and these are the ones that we're concerned about for this supply. So our plus minus 6 volts are derived from the plus minus 15 volts. Now, as I said, these were only 500 milliamp in the original design, so that's the total that we've got to work with in this part of the circuit. Now, I've upgraded them to 1 amp, so we've got a little bit more to work with, but the circuit will only draw what it requires. It's just a safety margin. So in our plus minus 6 volts, the components that do all the work are these 2 transistors, and they're exactly the same family as the one that works on the 5 volts. This time they're managed by a dual rail management chip, and there's some feedback here to set the voltage, so that you've got this pot that you can use to adjust the minus 6 volts that will match the resistor divider, the voltage divider that will feed back to the positive. So the positive set by this dividing network, and you're supposed to match the negative by using this one. Now, I've heard that in some AX-60s this pot isn't available, and so you're set with positive and negative 5.8-ish volts, and you just get what you're given. But on both of mine they had the pot, and this is the pot I adjusted to help my CEM chips tune. So this plus minus 6 volt rail is used for the voice chips, so the CEMs, and also the 4066 analog switches. So those 4066s switch on and off the noise or the external input. So they also use the same supply. After that, we've got 2 Zener diodes that are just a weak plus minus 5 volt supply that was supposed to be used for the analog chips only. So these would normally just feed the 4051s on the voice board, and they would be separate to the digital supply, because those 4051s, they pass a lot of our control voltages, so we don't want noise anywhere near them, or our control voltages that go into the sample and hold circuits might be affected. So it was a good idea to split them up, but then again, once you get to the main board, you'll see that they're actually tied together. So I suspect what's happened is AKAI have realised they don't quite have enough power on this 5 volt line, so they've borrowed some from the analog 5 volt, which looks like a bit of a last minute job. Now, the problem that we do have is that when I adjusted this supply to get me a little bit more negative voltage, which caused my CEMs to then magically tune on my original AX-60 with the original supply, adjusting that increased this voltage a little bit. But what happens is, because this Zener diode is managing the 5 volts, the more voltage we put in before the Zener, the more it has to shunt to get back to the 5 volts that it's supposed to be managing. So we end up with more current going through this Zener. And because of that manufacturing mistake where AKAI put this whole thing in a tube, it overheats. Now it's supposed to be rated at 1 watt, but when it's stuck inside a plastic tube, there's no way it's going to get to 1 watt. And in fact, even without increasing this voltage, these Zeners struggle. And if you get your AX-60 and you pop the lid and have a look for 2 Zener diodes in front of 2 transistors, I'll show you where they are. Where is that supply? Here it is. So hopefully we're in focus. So ignore the designations here because this one was modified before I got it. It looks like there were some last minute changes by AKAI. But I had these Zener diodes in these positions. But they were originally coming up off the board, which is what you would normally do when components need to get rid of a lot of heat, or you know that those components will have to dissipate a lot of heat. The convention is to raise them up off the board. So AKAI had them up here. And then to stop them bending over and shorting out and touching against anything, they're supposed to put the tube over the legs only, but they put the whole thing in the tube, so the tube goes right up here. So when you look inside your AX-60 and you look here, there'll be 2 black tubes, which is a real stuff up. Now, on my supplies, now, yeah, if you have a look at this one, you can see that 5 volt Zener I was talking about, that's still in the tube. See, that's wrong. That's a really big stuff up, but it doesn't affect this Zener because there's no current going through it. That one's just a safety for the 5 volts. So there were these Zeners with this plastic tube here and here, and they were both black. I couldn't even see inside the tube. Now on my other supply, they did this one right. I'll show you. This is one I've already salvaged to convert into one of my newer supplies. But you have a look here. This is exactly how it's supposed to be. You've got those plastic tubes just protecting the legs. And the Zener itself is free to dissipate all the heat that it wants. So that's what they should have did. They got it right here. And on the same board, they got it wrong here. See, both mine blew up. This was the one I was experimenting on. So, yeah, there you go. It's a lesson for you. So, we have to watch this Zener if we play with this one. So what happened after the last video when I adjusted this to give a little bit more power going to the CEMs on the negative rail, which is by this divider and this pot, what happened was that little bit of extra current, then that this Zener needed to shunt to keep the 5 volts the same, caused it to melt. Yeah, that should have been okay, but because of the tube it wasn't, so there's a fault. I suspect if you remove the tube you might be okay to do this adjustment and not replace the supply, but I don't want you to do that just in case, because there's a risk that it could still burn out. I think my suggestion is leave your supply the way it is, and I made a note in the previous video to do that. And if you are having tuning problems, it's best just to replace this whole part. Now I've had some people do that themselves and just tag a little circuit onto the board, but in my supply all of this is redesigned and you can adjust these to your heart's content without it blowing up. So it's probably better that you use my supply if you're going to adjust anything. So I think that's it for the original. Oh no, wait, there's one little circuit at the bottom here. So this is the whole supply, and right at the bottom we've got this little section with some transistors. Now this is actually the power on and off mute, and it's also the auto tune mute. So I think this transistor, so this is the main one that controls the mute relay, which is actually on the chorus board. Now to turn this one on and off, there's 2 transistors. One of them is the power on, controls the power on delay, and the other one receives a signal from the CPU to turn off when we do auto tune. Okay, so this one's responsible for turning this guy off when we auto tune, and this one's responsible for turning this guy off when during power on and off cycles. So this circuit has also been reproduced on my board. Different transistors, I've just used all the same resistors. I haven't bothered redoing the calculations. It seems to work fine, so that's it. Alright, so we finished the original supply. Whew. Okay, so here is the schematic for the supply that I designed as a replacement for the original AX-60 power supply. Let me zoom in. Oh no, hang on a second. First, I'll show you the section. So everything's relatively the same as what it was before. So you've got the mute section up here. You've got your 5-volt digital supply, and you've got your analog dual rail supply down at the bottom. So the layout should be fairly similar, and some of the designations I've tried to keep the same as well. So the main filter cap C1, C2, C3, I've tried to keep like the original, and these components up here. So let me now explain the details. So the first thing is that I've added some test points. The previous version of the supply was very difficult to test the voltages because you had to stick your probe inside the pins of the connector. It's much easier having test points. Now you can leave these as just pads, but particularly for the ones that we need to calibrate, I generally put pins in them so that I can use parrot clips so that I don't have to hold the probes on these points while I do the calibration. So you can do that too if you like. I'll show you on the supply once it's been built. So not much to say about the mute circuit besides that it's sort of the same. Well, it is the same. Relay in is the CPU, mute on, which controls this relay again, and then we've got the power, the feedback for the power switch on, which uses this transistor to send the mute signal out to the relay. Now the 5-volt supply is pretty much the same, just uses a modern regulator, LM317. We design with these regulators as if they are 1.5 amps, but that's the absolute minimum spec if they make a bad one. The typical is 2 amps, and you even go a lot higher than that. So there should be plenty of power here for the 5-volt line, and it should be regulated a lot better than previous. Some bigger capacitors on the output, and it's just nice to have a more modern regulator here. Apart from that, not much difference. The bridge rectifier is no longer a bridge rectifier. It's been split up into its individual diodes. I like to do that when the power's not too high, and splitting up the diodes means that they now aren't affected by each other, so they dissipate their own heat and they can be separated. So we can manage heat a little bit better by splitting them up, so they're not all heating the same die. Again, if you were doing a really big power supply, you would put this on a bridge rectifier that could be heat sinked, but there's no need in this case. So I've just upped these to 3 amps, separated them, and that should be more than reliable. That should pretty much work forever. Now I've done the same with the analog dual rail supply. I've split up using the same 3 amp diodes as in the 5-volt supply. So these are much higher rated than previous. And this was a tiny little bridge rectifier in the original version. I mean, it was tiny compared to the huge oversized one they put in the 5-volt line. So they're both, it's a good margin now on both of them, and they don't take up that much space because they've been split up. So the fuses remain the same. There shouldn't be any need to fuse higher than previous, even though the entire supply can provide a lot more power. That's more for stability rather than powering a small city. So our plus minus 15 volts now are 1 amp versions of those regulators. They used to be 500 milliamps, so I mean there's ample power now, so 7815 instead of 78M15. Next we have the lower voltage part of the circuit, so the plus minus 6 volts, which is derived from the 15. And there's a change here. I've added a Zener diode to drop the voltage a little bit before the regulator. Now this is a non-standard use of a Zener diode. Usually you would find them more like this. So if we have a look here, they would be reversed biased, and in this configuration, they would act as a voltage regulator. So any extra voltage above that reverse breakdown voltage would be shunted through, and what's left would go out. Now, it's not a very good regulator, but it does regulate, sufficiently for some circuits. Now up here, that's not the configuration. I'm using this sort of like a preconditioner, although normally a preconditioner would be a Zener diode like this, but with a transistor here, and that would act like a mini regulator, and a lot of the voltage would be dropped across the transistor, and you could put that transistor on a big heat sink. So as a preconditioner, you could remove a lot of heat by using a transistor and a Zener diode. Now I haven't done that. There's not a lot of room on this board, certainly not enough to put another heatsink on. So what I've done is I've decided to put a Zener diode here and have the voltage drop across the Zener diode itself help dissipate some heat before the regulator. So what we're doing is just giving the regulator a little bit of a break, just removing the top off that voltage before it gets to the regulator, and that means we have less heat dissipation through our regulator because there's less voltage drop. So this Zener diode is 3.3 volt, 5 watt. Now we're probably dropping about a watt or so, maybe 1.5, but that's just enough to get a little bit more heat out here, so we don't have to use as big a heat sink. We don't have a lot of room in this part of the board. So it's important that we try and use the space as effectively as we can. So I thought maybe removing a bit of heat before this regulator was a good idea. You can remove it if you like, but then you'll have the 15 volts here, and then a 9 volt drop across this regulator, and then 6 volts out. So dropping another 3 means we've only got 6 volt drop across the regulator. So it takes about 50% off the top, and I think that's a good idea, especially for longevity. Now when we talk about heat dissipation and junction temperature, which I'm not going to go into in this video, the idea is not to make components function properly, it's to make them last longer. So the lower you can keep the junction temperature in any semiconductor, the longer they last. And I think it's a square rule, so I think half the temperature, they last 4 times longer. So the lower you can get the junction temperature, the better. So I hope that this will end up helping this supply, but it's up to you if you want to use that Zener or not. Now, these two supplies, much easier to adjust than the original. Obviously, you couldn't even adjust the positive previously. It's just a fixed resistor divider network. But now we have a fine-tuned control over both, which means we can adjust pretty much whatever we want, but we need to stay within the limits of what the auto-tuned circuit expects. So remember, these plus minus 6 volt supplies go to feed our voice chips, our CEM3394s. If we adjust, say, the 6 volts too far, that auto-tune won't have the range anymore, because that chip will be the lower end of the octave range of the chip gets extended down, and for the same CVs we get lower notes. So we want to try and keep it the same as what AKAI designed it for. Now sure, that's not exactly what the chip was meant to do, but it's what the auto-tune expects. So just by giving this our normal 6 volts, these CEM chips just tune amazingly now. So there was a problem with the previous supplies just not supplying enough current or something. There must have been a voltage drop on the way to the CEMs. I don't quite understand it, but dropping this new supply in makes a hell of a difference to tuning, even when the voltage is the same. So there you go, there's quite a big difference there. You notice these diodes bypassing the regulators. They're just so the capacitors can discharge through them if the power supply is turned off. So that's something you'll see quite often. Then as we move along, we've got the plus minus 5 volts for our 4051s, for our analog 5 volt supply. These diodes have now been increased to 3 watts. So they used to be 1 watt. Not only that, they're no longer stuck in a blanket. So the tube, just don't use a tube on these ones. I doubt you'll find a tube that's big enough to put these in anyway. They're quite big diodes. But now we've got ample headroom here. So yeah, I don't expect these to ever die. So this supply should be much more reliable, much more capable of supplying more current than the previous one. I think we should get along and build it now and put one in an instrument and do a calibration. That would be awesome. Okay, building finally. So this should resemble your supply. The first thing you'd need to do is take off the connectors. So I've done that already. Here's one I prepared earlier. I just use desoldering braid. So like this stuff. It's fine, it works okay. I still don't have a solder sucker, but I haven't needed one yet. Okay, so connectors, and then we need the heatsink off. So the heatsink is a couple of screws underneath, and you'll need to undo the screws where the regulators are. You don't have to worry about taking the regulators off. You just want the piece of metal off. Unscrew. It's 5 screws. Now you want to keep the screws because they have the right thread to go back into the heatsink. And there's a trick here. When you put it back on, you need to make sure that the regulators are insulated from this piece of metal because they have different voltages on the main tab of the regulator. So here. So we don't want to short them out. They need to be isolated from each other. So you will need to use pads, and you will also need to use the washers. So these little washers that insulate the screw. They will be in the BOM as well. I'll do the best I can to give you the part numbers. These ones, I just got a packet from my local electronics shop which had the insulating pads and the washers together. They were from JCar. Can't remember the part number, but they'll only be relevant in Australia anyway. You might be able to find something overseas. Otherwise, these were element 14, which is fine now. You can get the washers and the pads separately. But I'll try and find some part numbers from Mauser and put it in the BOM. If not, they're just the TO22 package. So you just want to make sure that you get them for that package. It's TO22. Right, okay, and I've added some more fins on back of the heatsink here, just to make sure that we get that temperature down as much as we can. So all I did was just cut one up, put some thermal paste on the back, and then riveted it to the existing one. You've got to make sure if you do this, don't make it too wide, because the back of the synth sits about there. So ideally you don't want them to touch. That's another good reason why these should be insulated. You can't make this live in case it touches something. Okay, so that's what you need to do with the existing supply. I'll move these out of the way. Then you will get a board like this. So if you took the Gerber files and sent them to a PCB manufacturing place, you'll get back this exact board. Otherwise, you can take the schematics and the board files and modify it and do whatever you like. But my version looks like this. So what you need to do first is put all the components on that we don't get from the existing supply. So the resistors, the capacitors. Just leave the regulators for now. So don't do the regulators, but put everything else on. So after you've done that, it will look like this. So here's everything on, except for the connectors and the regulators. Now I can put the connectors on now. That's not a problem. I think these ones, the small ones, the original ones may be 2.5 millimeter pitch, but the connector I put in here is 2.54, which is a more standard version. So they still fit, but it just means that if you want, you can use some more modern connectors if you like. So it goes in with that. Gee, I'm not sure I can focus properly, but there's like an arrow shape on one edge, like a shorter edge with a point on it. They go to the front. Don't get them the wrong way around. There's no markings on this board. Maybe that's something someone else can add. So they go with that part to the front there. And I can't find the holes when I'm looking through a camera lens. There they are. So they're done. Don't forget to solder them on. Then what you would do is fit the heat sink first. Oh, actually it goes like this, and the screws come up through the bottom. So the existing screw would come up through the bottom like this. I don't have a screwdriver, so I'm just going to pretend. Oh look, I got it in a little bit, that's good. So they go in through the bottom, and then you would solder in the regulators. So what I usually do is attach the regulators to this first, or it doesn't really matter which way you do it. Like now you could just slot the regulator in here and then push it back. Make sure they're all insulated, and make sure the screws have their little insulating bits on them as well. Then once they're screwed in, then solder them in. Otherwise the height will be wrong for the heatsink. And these ones, attach the heatsink first and then put them in. So they're for the ±6 volt. And there's the adjustments for the ±6 volt. And here's the adjustment for that 5 volt, the high power 5 volt that goes to the CPU. So after you've done that, it's ready to put in the synth. Okay, so the power supply is now in the instrument. It's just the 2 screws you can see at the bottom of the heatsink at the back, and the 2 at the front. I've made those holes just very slightly larger, so it should fit no matter where the standoffs are. So before we plug it into the rest of the synth, we need to calibrate it. So first we just plug in the transformer. Just note at the orientation of that plug, make sure that you put it on the right way. And the first test that we want to do is actually just to make sure that we've got the 15 volts. So the 2 test pins here, there's 3. There's an analog ground in the middle. So our probe goes on that one, and also we want to test our other probe goes on the +15 or the -15. We can also get +15 for this plug here, which I've added. That's for the LEDs. So this plug here is useful for if you use the LED sliders. So that's where I plug that into. So I can also grab the 15 volts off that plug, which I will do. So firstly, we just want to see that we're alive. Okay, so I'll just turn it on. We're getting about 15 volts, slightly high, but that's a fixed regulator, so there's nothing we can do about that. I wonder if that's within the tolerance. Might check that later on. Okay, so we've got 15. Let me get the focus here. And we're going to test the -15. And we've got exactly -15, which is cool. So next, we just need to calibrate the ±6 volts. So that's this test point. I'll just get my screwdriver. And the adjustment point is the one that's, it's labelled on the board. I don't know whether you can see it, there's not enough light here, but it says +6 volt adjust. That's the one directly adjacent to the test point. So if I just put my screwdriver in there, and then we'll have a look at the screen. It's a bit low. So 5.8-ish is fine. I might even just set it at 5.9 for good luck. And okay, the negative. Okay, it's a little low as well. So this is what you'd expect when you first built the supply. It's not going to be, the voltages aren't going to be exactly where you want it. So okay, 5.9. Okay, and then the last thing to do is to calibrate the digital 5 volts, which is on this side. There's 2 test points here. So the bottom one is your digital ground and the top one is the 5 volts. So let me plug that in while the camera's busy out of focus. Okay, so we've got our 5. It's hard doing this with one hand. Okay, let's grab a screwdriver again. Get it ready. Okay, so, well, that's pretty close. If I could just leave it like that, there's really not much point trying to get 5.00 because you don't know whether the multimeter's been calibrated or not. So it looks like we're good. So next we just plug in everything, but I'll turn it off before I do that. And then we will do an on test. Okay, so we're all plugged in now. We have the plugs to all our boards and the main power for the LED sliders. It's very handy having that plug. I'm so glad I put that socket on the board. Okay, so what I might do is turn these lights off because it's reflecting quite bad. Okay, so we can see it a bit better now, although now I have a shadow. Okay, so the point here is the auto tune. We need to get a nice, good, quick auto tune with this supply. So I will turn it on. No smoke. Okay, let's do a quick auto tune and we'll see how quickly it tunes. So these are the voice LEDs. So this is it turning on the VCA for each. Oh, look, it's done already. So it was turning on the VCA for each voice, so it can get the feedback for the frequency as it tunes each voice. And that was over and done with quite quickly. Which is what should happen. So hopefully you have the same type of success when you build that supply, if you choose to build the supply. As I said, it's not needed. It's only really required if you're really having difficulty tuning and you've done all the normal stuff and you're not getting anywhere. And in that case, I found that in quite a few cases there is just a problem with the CEMs. Either they're aging or the power supply is bad and they just can't get to that first low frequency tune. I think it starts at the lower end of the frequency range when it first does the tune. And that negative supply is really critical to that first feedback. So we're done. Excellent. Okay, well, I think you probably won't see me with the AX-60 until I put the two together. So I'm planning to combine my two AX-60s into one big AX-20. So on the other one I will take the keyboard off and I will just take the panel and I will mount it just above this panel, probably sitting a little bit upright like an MS-20. So I have two voice layers of two AX-60s controlled by one keyboard. So the idea is to have like a CS80 type arrangement where you've got two voice layers that play on top of each other. That would be super fat, super awesome. I really do like this synth. Yeah, it's cool. I think it's cool. Alright then, that's it for me, and I will see you in the next video.